Hello, my name's Ilija. I'm a current DPhil student at the Department of Materials at the University of Oxford under the supervision of Professor Kyriakos Porphyrakis. And today I'm going to lead you in on some state secrets for how we make the world's most expensive material. Humankind seems to have some sort of morbid fascination with wealth and monetary excess. Ask different people what the most valuable thing in the world is, and I'm sure you'll get different answers. Great monarchs of the past, such as Catherine the Great, may have said their crown jewels. The buyer of the world's largest flawless diamond would certainly say that. Floyd Mayweather would definitely have his own opinions. At the Department of Materials in Oxford, at our lab, we have actually created the world's most expensive material. Officially by weight, this used to be californium, a man-made radioactive transuranic metal. Sold for about $30 million a gram, but we have quite easily surpassed that, and today that is what I'm going to tell you about. We work with a family of materials called fullerenes. These are a alternative structural form, what we call an allotrope of carbon, just like diamond and graphite. And they are in the shape of a closed cage. Now, these were named after a man called Richard Buckminster Fuller. So their full name is the Buckminster fullerene, often called buckyballs. Now, he had nothing to do with the discovery of this molecule. He was not a chemist. In my mind, he was one of the 20th century's greatest thinkers. But the guys who discovered this material basically paid homage to him because Richard Buckminster Fuller was famous for popularizing geodesic domes. If you've ever been to the Eden Project in Cornwall, then you will certainly have seen them before. Now, geodesic domes and fullerenes share a very important structural feature. And you can see that they are primarily composed of hexagons, but every now and then there are some pentagons which appear. And these are very, very important, for they introduce strain into the structure and force this curved shape, if you like. Without the pentagons, we would simply have a planar hexagonal sheet, just like graphene, the layers of graphite. So that is a very important thing for how fullerenes are, for the structural form of fullerenes. Now, the fullerenes, or the most abundant fullerene rather, C60, because it has 60 carbon atoms in it, shares a remarkable similarity to an old school football. In fact, it's more than a remarkable similarity, it is precisely the same shape, what we call a truncated icosahedron. And in this shape, every vertex of the football corresponds to a carbon atom in the fullerene. Every edge corresponds to a bond between carbon atoms, and there are precisely, I can tell you, 20 hexagons all separated by 12 isolated pentagons. This I find mind-blowing, given that a fullerene is only 1 nanometer across, about 7 orders of magnitude smaller than a football. Now, I've said here that the fullerenes are a family of materials because actually we can get them in different flavors. So C60, when we dissolve it in solution, is typically a beautiful bright purple color. Now, we can actually add more carbon atoms to the cage and get, for example, C70, which is red like wine. And you can go higher and higher to C84, for example, which is a nice greeny yellow. So, how do we actually make these materials? This is where the fun starts. So, what we have here is an image of our setup in our lab. It's a process called arc discharge. And basically, the discoverers of this material first spotted an odd, if you like, what we call a spectroscopic signal from space. And they tried to recreate these synthesis conditions, so a small portion of the galaxy, in the laboratory. So in the process of arc discharge, we effectively have 2 giant thick pencils, 2 graphite rods, which are placed very close to each other in a helium atmosphere. We blast a huge direct current through the graphite rods, and a spark, or an arc if you like a piece of lightning, jumps across the gap, and a plasma is formed about 5,000 degrees Celsius, and in this terribly violent process we actually get these beautiful small fullerene molecules being formed. A black soot is formed around the outside of the chamber. We sweep this black soot up, dissolve it in solution in various solvents, and we can then separate the fullerenes from the rest of the carbonaceous soot. We do this using a process called chromatography, specifically high performance liquid chromatography. Now here, if you've ever done done an experiment in a school chemistry lab where you separate the inks, different coloured inks in a felt tip pen using various solvents on a piece of paper. It is precisely the same technique, just a lot more high tech. So rather than a piece of paper, we have a column which is filled with silica. So we inject our solution into the machine. The solution passes through a silica column, and depending on the size of the fluorines, they separate out, and we can isolate these beautiful coloured solutions with pure different fluorine components within. Now, once we have these various materials, we then come to the crux of how we actually make the world's most expensive material. As I said before, fullerenes are closed carbon cages. We can actually think of them as molecular prisons because inside we can capture and incarcerate different species. These have been done with lanthanide metals and even with water in some very good work from Japan. What we do in our lab is capture atomic nitrogen. This is quite incredible. Atomic nitrogen does not exist in the natural world because it's very reactive. Although the air around us makes about 78%, or is comprised rather 78% nitrogen, that all exists in its dimeric form, in N2. So achieving the isolation of atomic nitrogen, and this is all stored at room temperature, is really quite incredible. So this is what we call an endohedral fullerene. That means that we have something inside the molecular prison, within the cage. So, how do we actually get nitrogen inside? It's a process called ion implantation. And in this process, we sublime our C60 fullerene, which means that it goes from the solid to the gaseous phase in one go. At 90 degrees to this sublimation, we fire nitrogen ions. And we have to hit the sweet spot in terms of the energy of the nitrogen ion in order to shoot it into the fullerene cage. My supervisor likens this, actually not completely incorrectly, to firing a bullet at a bullet. The likelihood of the nitrogen ion going into the C60 cage is not very high. Typically, in an unrefined process, it's about 1 in 10,000. This is the key to why this material is so expensive. So, once we have completed the ion implantation stage, only 1 in 10,000 of these fullerene cages actually has anything inside. So we have to go through another round of HPLC, chromatography. But this time we're separating C60 from N at C60, the at symbolizing that the nitrogen is within the cage. So these are two very similar molecules. The nitrogen does not interact with the cage that much. And given that both the C60 cage is the same size as an empty C60 cage, it's very difficult to separate. So we actually use, rather than a standard HPLC column, a rather juiced up version. And in fact, you can see the difference between the two columns which we use. The fatter one is used for separation of N at C60 from C60. And we have to pass this through multiple times, recycling the solvent in order to separate out the two species. This takes a lot of manpower, a lot of machine power, and a lot of solvents. This is the key to why the material is so expensive. Now, this is precisely the process which we use in our lab, and my supervisor, Professor Porphyrakis, has spun out the production of this into a company, Designer Carbon Materials. When we first made our first batch towards the end of 2015 and sold this material, the internet went crazy. So you can find anywhere online to verify my claims that we do actually make the world's most expensive material. And I can tell you that we sold the equivalent of 200 micrograms, that is 6 orders of magnitude, or rather 4 orders of magnitude less than a gram, for 22,000 British pounds. This works out at 110 million pounds per gram, making californium look quite paltry in comparison. So, all well and good. Why do we actually want to make this material other than bragging? So, the key one is for quantum computing. This is a massively more powerful way of doing computing based on what we call quantum bits or qubits rather than bits. A bit in classical computing can take a value of 1 or 0 and you do your binary computation that way. In quantum computing, a qubit can take a value of 1 or 0 or potentially both at the same time. It's this power of quantum mechanics which we look to exploit. The isolated nitrogen atom is perfect for this situation, and we can actually exploit a property of that atom called spin. And by exploiting that, it's isolated from the environment, and it has a long enough, what we call coherence lifetime, in order for calculations to be carried out. A second application is in the use of atomic clocks, and not only normal atomic clocks, but miniature atomic clocks. Typically, atomic clocks currently use rubidium and cesium atoms in the gaseous phase. And because it's in the gaseous phase, these machines take up a very large space, typically the size of a room. You can get smaller ones now. And atomic clocks use a natural standard. It's the internal standard of what we call an energy transition within the atom. This is compared to mechanical clocks, which use quartz crystals, where any manufacturing error leads to a timekeeping error. These are set by nature, atomic clocks, and so they are very, very accurate. Now, with NHC60, again, we can utilize the isolated nitrogen, and actually we can utilize this in the solid state or potentially even the solution state. Either way, these are far smaller than gaseous state atomic clocks, and so we could potentially use them in a wristwatch. This is very important for military applications where there is not a very strong GPS signal, and other things such as seismic monitoring. The realization of both of these applications would lead to a technological revolution. And so it's of paramount importance that we try to reduce the cost of this quite fascinating material. And that is something which we are working very hard at doing over in Oxford. Thank you very much.